Hey, welcome to AP Calculus Chapter 4, Section 1B. I did not do a Section 1A, some beginning chain rule problems, but hopefully 1B suffices. If not, you can come and ask some questions. Maybe I'll put a 1A together. We're going to find ds dt, so the derivative of function s with respect to t. I have a mother function here. So ds dt, treat the mother, derivative of cosine is negative sine of, leave the baby alone, and then treat the baby. Don't forget, pi is not a variable. This is just a constant. This might as well be 8, the whole thing. What's the derivative of 8? 0. What's the derivative of negative 3t? Negative 3. Now, make certain that you're making that a pronounced times when you're doing these chain rules. Otherwise, all of a sudden, that negative 3 just gets viewed as a minus 3. So simplify ds dt. I've got this times this. This is a negative times a positive, or times a negative gives me positive 3 sine pi on 2 minus 3t, and that is it. Okay, sometimes people look at a problem like B, and once again they'll think, okay, I got to find the derivative of this. So that's a function times a function. Well, technically 4 on 3 pi is a function, but I don't have to deal with that. It's just a constant. Pi is a constant, so if I have a constant times something, times a function of t, the constant just survives. ds dt is 4 on 3 pi times derivative of sine of 3t. Now I have a mother function, sine. Its derivative is cosine of, leave the baby alone, treat the baby. Derivative of 3t is 3. Plus 4 on 5 pi survives, derivative of cosine, negative sine of, leave the baby alone, then treat the baby. So let's clean things up. ds dt, 3, plain old 3 times 4/3, 4 on 3 pi is 4 on pi. 3's cancel. Cosine 3t. 5 times 4/5, 5's cancel, plus 4 on pi. Oh, we got a minus in here as well. Sorry. Minus 4 on pi sine of 5t. Okay. Perhaps, if you're looking to match back in the book, perhaps they might factor out a 4 on pi. Not necessary. In fact, I could argue either way. One's more simplified than the other. This has, less factors included in it. I mean, it doesn't include that twice, but this is multiplied out. Either one. Either one I'm fine with. Okay, dr dt. We want dr, derivative of r with respect to theta. So here we have an outside function and an inside function. We're going to take the outside derivative, secant squared of the inside function, times the inside derivative. And the derivative of 2 minus theta with respect to theta is negative 1. So dr d theta is negative secant squared of 2 minus theta. Okay, this one may be a little bit tougher here. You might want to think of this as theta sine of theta to the 1/2. And then it becomes pretty clear, dr d theta, we've got an outside function, something to the 1/2. And the derivative of something to the 1/2 is 1/2 something to the negative 1/2. But leave the baby function alone. And now treat the mother function, and be careful with this guy. This is a function of theta times a function of theta. This is a product rule. So times all of plain old first times derivative of second plus derivative of first 1 times plain old second. Or dr d theta equals, what stays in the numerator? 1 times theta cosine of theta plus sine of theta what goes to the denominator? 2 is already in the denominator, and then we have square root of theta sine of theta. And I like using square root down here rather than to the 1/2 because the problem started with square roots, kind of establishing a convention. Okay, let's move on. You will need to use chain rule 2 or 3 times in each case. We might want to look at this as sine of 3x minus 2 squared. And that makes it pretty clear that our outside function is something to the second. So 2 times something to the first. Leave the baby alone. But then treat the baby. It just so happens that the baby is also a chain because there's a mother function here and a baby function. So derivative of sine of this is cosine of this times derivative of this, or the outside derivative of the inside function times the inside derivative. And we end up with, let's see, I got a 2 times 1 times 3, I've got a 6 times sine of 3x minus 2 times cosine of 3x minus 2. Anytime sine and cosine of the same argument are together, you have the possibility that the back of the book answer might invoke a double angle trig identity. So if you have something there that pops up, don't hesitate to ask questions. I believe this is a good answer. I'm not checking the back of the book answer right now to try to match it. Okay, B. dy dx. Pretty clear here. We've got an outside function, 2 something to the, something to the second. The derivative of that would be 2 something to the first. That's 1 plus cosine 2x. Leave the baby function alone. Then treat the baby times all of, well, derivative of 1 is 0. Derivative cosine of something is negative sine of something. But inside function 2x. Treat the baby times 2. So dy dx, let's not lose track of that negative sign we had in there. 2 times a negative 1 times a 2. That's negative 4 times 1 plus cosine of 2x times sine of 2x. I don't know why I put the parentheses. Could have gotten away without them, but could add a pair there to make it match. All right, moving right along. dy dx, I have an outside function sine. The outside derivative then is cosine of, leave the baby function alone, cosine 2x minus 5. Now find the derivative of the baby function. Well, the baby function has a mother function. In other words, we kind of got a pregnant baby right here. Cosine, we got embedded functions. So I need to find the derivative of all of this. I just peeled away that outside derivative. Derivative of cosine is negative, pronounced times, negative sine, leave its baby alone, and then find the derivative of that baby, 2. So dy dx is, I've got a 1 times a negative 1 times a 2, negative 2, cosine of 2x minus 5 times sine of 2x minus 5. All right. Might want to look at this as cotangent of 2x to the 1/2, but that 1/2 is only acting on 2x, so it's not cotangent of something to the 1/2. And now that makes it clear that our outside function, our most outside function, is cotangent. So the derivative of cotangent, negative cosecant squared of, leave the baby alone, treat the baby. Well, the baby has an outside function, something to the 1/2, so that is 1/2 something to the negative 1/2. So leave the baby alone. When the baby's born, treat the baby times 2. Let's see what we've got. dy dx. Let's look for constants. Negative 1 times 1/2 times 2, negative 1. I've got cosecant squared. Maybe I'll write this as square root of 2x now. All over square root of 2x. Can we cancel those square root of 2x's? You better not. This is in a function. This is a factor, but this is not a factor. It's in a function. Alrighty, moving right along again. Find the second derivatives, and these things start out seeming pretty nice, but they can get a little bit ugly. So we're going to find first derivative. I'm just going to call it y prime. Derivative of tangent, secant squared of x, which we might want to think of as secant of x squared. That makes the mother-baby analogy pretty clear. So the second derivative, the mother function is something to the second, 2 times something to the first, leave the baby alone, secant of x, treat the baby, secant's derivative is secant of x, tangent of x, so y double prime can be simplified to 2 times secant squared of x, tangent of x. Now it's possible that the back of the book might take secant squared and turn that into 1 plus tangent squared of x and distribute just to get everything in terms of tangents. Just to be alert, we're still to match answers, and I want you to do it. I believe this would be fine on AP test, but to make certain that we're in good shape, and plus just for the practice on our trig rules, try to match the back of the book answer. Okay, similar. Y prime equals derivative of cotangent of 3x, outside derivative of, so the derivative of cotangent is negative cosecant squared, leave the baby alone, treat the baby. So I get y prime equals negative 3 cosecant of, I'm going to write it this way, you'll see, you might catch on right away, if not you're going to see why in just a second. When I write that squared out here rather than there, it makes it really clear that my outside function, forget about the negative 3, it's just going to survive. It's a constant times a function of x. My outside function is something to the second. So y double prime, this becomes 2 times the negative 3, negative 6, leave the baby alone, cosecant of 3x minus 1, and reduce the power by 1, and now treat the baby. Derivative of cosecant, so times negative cosecant, leave the baby alone, 3x minus 1, I'm running out of room here, cotangent of 3x minus 1, and treat the baby times 3. My apologies for pinning myself in there. So what do we end up with? I've got a negative times a negative, that's positive 6. This is times a 3, not over. This is times a 3 here. Negative times negative, positive 6 times 3. I get an 18. I've got a factor of cosecant 3x minus 1. I've got another factor of cosecant 3x minus 1. So squared here, and I've got a factor of cotangent 3x minus 1. Now once again, because cosecants and cotangents live together in a Pythagorean, it's possible cosecant squared 3x minus 1 might be replaced with 1 plus cotangent squared 3x minus 1, and then distribute and combine some things. Okay. Find the value of f of g. That's f of g of x. And we got all these u's in here. But this says, they're going to talk about f of u. That's just a u substitution. But they're telling us that u is some function of x. And oh, by the way, u is just square root of x. So f of g f of u is just f of g, and f of g is f of square root of x, and f of square root of x is square root of x to the 5th plus 1. We might want to think of that as x to the 5 halves plus 1. So f of g's derivative, as they're asking for, is just the derivative of this guy. So that is 5/2 x to the 3/2 plus 1. How might the back of the book have that answer? Well, they might present this as, this could be 5/2 times the square root of x to the 3rd plus 1, or maybe 5/2, if I take two of these square roots, 5/2 x times square root of x plus 1. Lots of options at that point like this, but I kind of like this as well since they started out talking about square roots. I think any of those acceptable. Oh, plus 1 doesn't survive though, does it? Plus 1 does not survive the derivative process. I'll bet you caught that. Okay. So, is it clear? U is g of x, but g of x is 10x squared, so I just want f of 10x squared. And f is a factory that takes things and puts them right here. So 10x squared into there, I get 2 times 10x squared on 10x squared squared, puts things right there, plus 1, or 20x squared on 100x squared, x to the 4th, excuse me, x to the 4th plus 1. Now we need to find that derivative. If it was a pre-calculus problem, you'd be done now. You find f of g, but now we find f of g's derivative. F of g's derivative is, clearly, we are in a quotient rule here. So I want low d high, derivative of the high function, 40x, minus high, 20x squared. D low, derivative of the low function, is 400x cubed, all on the square of the thing below. Let's get some simplifying done in here at least. In fact, it looks like we're going to get some, I might use a sidebar for this. It looks like we're going to get some x to the 5ths here, combined with some x to the 5ths there. So 40 times 100, I get 4 times 1, 4 with 3 zeros. I got that many x to the 5ths. And over here I've got minus 2 times 4, 8 with 1, 2, 3 zeros, x to the 5ths, for a total of negative 4,000 x to the 5th, but I also have a plus 40x here, all on the square of the thing below. All on the square of the thing below. So this is 100x to the 4th plus 1 squared. All right, example 6. See how we're doing on time here. I'd like to get this done in one shot. What happens if you write a function as a composite function in different ways? Do you get the same derivative each time? Okay. So find dy dx if cosine y is this, by writing y as the composite of, let's say y is cosine, u is this. So in other words, y is our outside function cosine, and our inside function is the whole. That's the way we would typically do it. So I dy dx. We're looking at this. I'm just going to write it like this: cosine of 6x plus 2's derivative equals, oh, no problem, outside derivative, negative sine of inside function 6x plus 2 times the inside derivative 6, or dy dx equals negative 6 sine of 6x plus 2. Okay, now they're saying, let's think of this like this: cosine of, this is for double I, 2 times 3x plus 1. And they're really thinking of this thing as cosine of 2 times an angle. So if I did cosine of 2u in this case, cosine of 2 times u, my derivative here would be, so if I said y equals cosine of 2u, my derivative would be cosine, derivative of cosine, negative sine, of 2u times 2, treat the baby, or negative 2 sine of 2u. And then u is 3x plus 1. If I put 3x plus 1 in here, I get negative 2 times sine of 2 times 3x plus 1, and I get negative 2 sine of 6x plus 2. And why didn't I match here? Cosine 2u. Oh, derivative of, I still need the derivative of this. I still need the derivative of 3x times 3, and there's our negative 6. I need to come back and clean that one up, and we'll do, and I will take care of that in class. But I could approach that another way, but I want to get this video out tonight. What is the largest value possible of the slope of? Oh, I don't know. Seems kind of crazy, but let's go ahead and find the slope formula. dy dx, they're talking about slopes. Derivative of sine, cosine of x on 2 times the inside derivative 1/2, or 1/2 cosine of x on 2. Well, what is the largest derivative or the largest slope we can have? Well, this is the slope. And what is the biggest value that cosine of x on 2 times 1/2 can have? This has no effect of it on the graph of cosine whatsoever as far as how tall it gets, but this does. This is half the amplitude, and cosine, typically the biggest value of cosine is 1, so half that size. Since our amplitude equals 1/2, then the largest value we can get for slope is 1/2. This is a graph that the graph of this only goes up to 1/2, or something along that line. This is half as fast, so this would actually be 4 pi. But it only goes as high as 1/2, excuse me. Okay, number 8. Find the lines that are tangent to, all right, this is so much what we do really just leads to this. So I guess we need dy dx here. So the derivative of this, the outside function could be thought of as 2 tangent. So the outside derivative is 2 secant squared of pi x on 4. Treat the baby. The derivative of pi on 4 times x is pi on 4. So there is our slope formula. Well, we want the slope at x equals 1, so I want, it's kind of like saying f prime of 1 equals 2 secant squared of pi on 4 times 1 times pi on 4. Okay, secant, let's go to cosine graph. I'm going to go to cosine of pi on 4. I'm just going to build a triangle at pi on 4. Pi on 4, we got a 1, we got a 1, we got a root 2. So cosine of pi on 4 is x on r, 1 on root 2. Therefore, secant of pi on 4 is root 2. So I get 2 secant of pi on 4 is root 2 squared times pi on 4. What good happens here? 2 times 2 times pi on 4. 4 times pi on 4 is pi. So that is our slope, or our f prime is pi, and we are at a value x equals 1. At x equals 1, what is f of x? F of x is 2 times tangent of pi on 4, tangent of pi on 4, 1 on 1, 1, so we get a point 2. So we have the point 1 gives us 2, and the slope is pi. So the tangent is y minus the y coordinate 2 equals slope pi times x minus the x coordinate 1. We could certainly put that in slope-intercept form. And the normal is y minus 2 equals opposite reciprocal, negative 1 on pi times x minus 1. All right. And I am going to have to do this at another time. I am running out of time here, so I will have to add on example 9, so you can look for a part 2 of this 4B, a part 2 video, and that will be coming up soon. Thank you.